Hello all, I am Professor Chetan JD, Assistant Professor, Department of Mechanical Engineering, MIT Mysore. Today we are solving problems on wind energy. So let us take up the first problem. Wind at 1 standard atmospheric pressure. So is given atmospheric pressure. Of course, all the wind turbines will have the pressure as atmospheric pressure because they will operate in atmosphere only. And 20 degrees centigrade, he has given you the temperature as well. So pressure is 1 atmospheric pressure. We know that 1 atmospheric pressure is 1.01325 bar. So that if you multiply it by 10 power 5, you convert it into Newton per meter square. And he has given the atmospheric temperature as well, that is 20 degree. Convert it to Kelvin, add 273, you get 293 Kelvin. Has a velocity of 12 meter per second. He has given the velocity of the wind. So generally we denote velocity of the wind as V suffix I, that is velocity of the wind at the entry of the turbine or inlet of the turbine. So V suffix I is 12 meter per second. The turbine has a diameter of 120 meter. Turbine diameter is given 120 meter. Operating speed is 40 RPM. Operating speed is given, that is 40 RPM, that is revolution per minute at which the rotor is turning. At maximum efficiency, so these values whatever he has given, it is at maximum efficiency, that is RPM what he has given is at maximum efficiency. Now he is asking you to calculate total power density, maximum power density, obtainable power density. He has given, assuming the efficiency of 35%, then you go for finding out the torque and total power. What he has given, in order to calculate total power density, we already know the power formula. Power formula for wind energy is given by half into rho A Vi cube, half into rho A Vi cube. But if you bring the area here, that becomes power density. Generally the power density unit is watt per meter square. So if we take the A here, what you will remain with is half into rho Vi cube. So this is power density, the unit will be watt per meter square. If you are calculating power, A you are substituting it here, then unit becomes watt. So in order to calculate this, what are all the unknowns we have? We need to have density, we need to have inlet velocity. We already have the inlet velocity in meters per second, that is 12 meter per second. Density is not given to us directly, even though we know the density directly. Generally we say 1.23 kg per meter cube. But he wants you to calculate the density by using the data here, that is atmospheric pressure and temperature is given. So we need to calculate the density if the values of pressure and temperatures are given. So how to calculate it? We know that ideal gas equation, PV is equal to M RT, where you can send the volume this side, P is equal to mass by volume into RT, where mass by volume itself is density. So P is equal to rho RT, or you can simplify this for rho, then you will end up with rho is equal to P by RT. So this is how you have to calculate density when pressure and temperature is given. For that pressure and temperature, because the density is a variable parameter depending on pressure and temperature. For atmospheric conditions, we generally assume the value as 1.23 kg per meter cube. However, even if you substitute, the value will be nearer to the value which we used to have. So pressure you substitute at this pressure, and R is the gas constant which we know. For air it is 287 and temperature is 293 Kelvin. We get the value of 1.2 kg per meter cube. Now come back here, all we did this here because we wanted the value of density. We got the value as 1.2 kg per meter cube. Substitute here half into 1.2 into Vi cube, that is 12 power 3. If you substitute this, this is the total power density. Now in order to get the maximum power density, we have derived the formula. Maximum power density is always only 59%. So that is 0.5925 of the total power density. So 0.5925 into this value, that is P total by area, 0.5925 into 1036.8, we get the value of maximum power density. This is the maximum power density. If you multiply the area this side, it becomes maximum power. But however, he has not asked that. Maximum power density he is asking. So get this value by multiplying the actual power density by 0.5925. So that next, obtainable power density. How much we can obtain? Now this is the question. Efficiency is given to you. Efficiency is 35. So here he is indirectly telling you this is what is obtainable. Efficiency he has given means if you multiply the value with obtainable efficiency, you get an obtainable power density. So efficiency into P total by area, that is total power density, we get obtainable power density. If you multiply the total power density with the efficiency, we get obtainable power density. So we got these values now. We will move on to the second part. So since you have got this value by the given condition, efficiency as 35%. So next, if you use these value in any of the calculation, these unknowns will be based on efficiency 35%. So from here onwards, for calculating these two, if we use this, it will be considering efficiency as the 35%. Now go for total power. As we discussed, total power is nothing but half into rho A VI cube, or if you multiply this term with the area, you get the total power. So P by A, power density into area, pi d square by 4. So remember, while substituting this here, power density, we are taking maximum obtainable, that is considering 35%. So obviously what we get is, if you know this diameter is 120, you get total power as this much, 4104.076 kilowatt. Now go to the total torque. Torque also we have derived the formula. Torque is equal to 2 by 27 rho diameter VI cube by N. So remember, here you are substituting velocity in meter per second. So this value of revolution per minute also has to be substituted in meter per second, because ultimately we want the unit Newton. Remember, here torque means he is talking about the force, not Newton meter. Substitute it in, get the answer in Newton. If you substitute all the values in the appropriate units, that is density in kg per meter cube, diameter in meter, velocity in meter per second, and this in second, we get the unit kg meter per second square, that is Newton. So get this value, that is torque is given by 27648 Newton. Let us solve the problem number 2. A horizontal shaft propeller type wind turbine is located in area having the following wind characteristics. So this doesn't matter much to us. We want the characteristics of the wind, because all the formulas which we have with us doesn't take into account whether it is a horizontal or vertical axis turbine. So this is what is the limitation of our subject itself. So the speed of the wind is 10 meter per second. So speed of the wind is given Vi, V suffix I is the speed of the wind. V suffix I is 10 meter per second at 1 atmospheric pressure. So pressure will generally be 1 atmospheric pressure only. So pressure, which we know the value as 1.01325 into 10 power 5 Newton per meter square, that is the atmospheric pressure, and temperature is 15 degree Celsius. So temperature is 15 degree Celsius, but in order to substitute it in any of our equation, We need it in Kelvin. So add 273 to convert it into Kelvin. Remember, whenever these two data are given, he wants you to calculate density by using these values, not to use the assumption value as 1.23 kg per meter cube. So air density has to be calculated by the ideal gas equation using atmospheric pressure and temperature. So now calculate the following: total power density in the wind stream. Total power density is asking in watt per meter square. Maximum possible obtainable power density, we already have the formula for that also. Then actual obtainable power density, if the efficiency is 40%, we can easily calculate this by multiplying whatever the value you have got by 40%. Total power from the wind turbine, and he is giving you the diameter. Now, in order to calculate total power density, we have this formula P total by area. So area has been taken this side because he is asking you the power density. We want it in watt per meter square. So area will be this side. P total by area is equal to rho Vi cube by 2, where rho is the density of air, which is not given to us directly. So how should we calculate it? In order to calculate the density, we need to use the ideal gas equation. We need not to write all these steps. If you remember, this rho is equal to P by RT, that is sufficient enough to calculate this value. So however, PV is equal to mRT, or P is equal to m, V I will send this side to the denominator m by V, where m by V is density is equal to mass by volume. So this is nothing but density. So P is equal to density into RT. R, you want rho, right? So remaining terms I will send to the other side. So rho is equal to P by RT. Substitute pressure as this value. R value, which we know for air, it is 287. This need not to be given to us because this value is the gas constant for air. R for air is 287 joule per kg Kelvin. So R value, which is already known for air, temperature is given, calculate density, which you will get it as 1.226 kg per meter cube. Next, we did this because we wanted the density value here. So we got the density. Now go for total power density is P total by area, that is rho Vi cube by 2. Now rho we have 1.226, and Vi cube, velocity of the wind is given as 10 meter per second. So 10 power 3 divided by 2, you get the total power density as 613 watt per meter square. Total power density in the sense the power density which is there in the wind. Okay. Now we will go on to the sub question 2. Maximum possible obtainable power density in watt per meter square. We have derived an equation for maximum power density in a wind turbine. The maximum power density is given by this equation, 8 by 27 into rho Vi cube, or if you simplify this, it is 0.5925. This rho Vi cube is nothing but P total by area. So 0.5925 into this value will give you maximum possible power density. So 0.5925 into 613 will give you 363.2 watt per meter square. Look at these two values now. This is the total power density, but maximum what we can get is 363, but actual will be lesser than this value. So this is the maximum what you can get. This is the power available in the wind, power density which is in the wind. This is maximum power density which we can get, but the actual will be much lesser depending upon the efficiency of the conversion, which he has given you. Third one, calculate actual obtainable power density in watt per meter square assuming 40% efficiency. So actual obtainable power density is given by P by A is equal to efficiency into what is available in the wind, that is 0.4, that is 40%, into 613, you will get 245.2 watt per meter square. This is what you can actually get considering 40% efficiency of the conversion. Next, he is asking you total power from the turbine considering 120 meter diameter. So, total power is equal to power density into area. This is in watt per meter square. This will be in meter square. If you cancel it, meter square will get cancelled. You will get here the unit as watt. That is what we want. So, this is power density 245.2. So, we are using actual because we want the actual power here, total power. So, 245.2 into area considering the diameter as 120, which he has given. So, 120 square, you get this value as 2773.146 kilowatt. We will go for the third problem. Wind at 1 standard atmospheric pressure. So, pressure is given 1 atmospheric pressure, which is 1.01325 into 10 power 5 Newton per meter square, and 15 degree Celsius converted to Kelvin, 15 plus 273, 288 Kelvin, has velocity of 15 meter per second. So, Vi, we denote the inlet velocity as V suffix I, Vi is 15 meter per second. The turbine has a diameter of 120 meters. So, diameter of the turbine is given 120 meter, and its operating speed is 40 rpm. So, we denote rpm by capital N. So, N is equal to 40 rpm at maximum efficiency. Calculate, first one, the total power density in the wind stream. So, we have to calculate the total power density. Second one, maximum obtainable power density. Third one, total power and torque assuming efficiency as 35%. So, we have got the data. In order to calculate the total power density, P total by area, we know the formula, half into rho Vi cube. But always this value will not be directly given to us, that is density. We will have to calculate by temperature and pressure, which will be given to us normally. So, using this ideal gas equation, PV is equal to mRT, you end up with P is equal to mass by volume into RT, where mass by volume can be written as rho. So, that is P is equal to rho RT, or simplify it for rho is equal to P by RT, where pressure is known to us 1.01325 into 10 power 5 Newton per meter square, or you have to substitute it in joule per kg Kelvin. This is the known value. He may not give you this value. We will have to remember the gas constant for air is 287 joule per kg Kelvin. So, 287, and temperature should be substituted in Kelvin. 15 plus 273, we have got 288 Kelvin. So, if you simplify this, you get the density as 1.226 kg per meter cube. Even the the known value as 1.23 kg per, it is quite nearer to that value. But always whenever this data is given to you, it is expected that you have to calculate the density by using pressure and temperature. Next, total power density, we will go, all we did calculate the density for using it here. So, substitute that density here, half into 1.226 into velocity 15. So, Vi cube 15 cube, you get the total power density in watt per meter square, that is 2068.87 watt per meter square. Next is maximum obtainable power density. We have derived the equation for this, 8 by 27 into rho Vi cube, or 8 by 27 is nothing but 0.5925. So, this is the derived equation. This is what is available in the wind, and what is maximum obtainable from that wind power, that is given by only 59% of the total power can be obtained in the from what is the power available in the wind. So 0.5925 into P total by area, which we have got it here. So 0.5925 into this value, you get 12226 watt per meter square. It is nearly 60% of what this value is. This is power available in the wind. What is the maximum amount which you can extract? This is maximum, theoretical. It will be even lesser than this. Actually, it will be lesser than this. This is the maximum value. Remember, if you get any answer above this value, that means it is impossible. So it has to be lesser than this value. Next, we will go on to the third question, that is total power and torque, assuming efficiency as 35%. Efficiency is 35%, that is what we said. This is maximum available. Now, only 35% is what we can get in this particular wind turbine. So, if at all, if you are getting this value should not be greater than this value. But however, this is in kilowatt, don't worry, we are calculating it power. If you calculate the power, this power should not be greater than this power. Now, total power assuming efficiency as 35%. Now, in order to get the total power, this term has to be multiplied with area, that is pi d square by 4. So, this is total power into efficiency. So, if you multiply with 0.35, that is 35% of the actual or total power, you get 8184 kilowatt. So, if you want to compare this also has to be in power, not power density. So, we cannot compare it simply. Now, go for torque. So, torque is given by 2 by 27 into rho d Vi cube by N. Substitute all the values which we know. What we get is, but remember, RPM should be converted into RPS or per second, because velocity you are substituting it in meter per second, because ultimately the unit what you have to get here is in Newton. So, if you substitute density as kg per meter cube, diameter as meter, velocity as meter per second, and this as revolution per second, you get kg meter per second square, which is Newton. So, finally, the torque what you can obtain is 55,170 Newton.